Okay, so hi everyone. So I'm Nicolas Gambas, principal privacy engineer at Sandbox AQ, and yes, so working a lot on different privacy preserving techniques these days. And today, so I'll present a new result. So this is a joint work with co-authors of Maria Georgieva-Belorge, Sergiu Karpov, Sandra Aguash, and Dimitar Jetchev. So two of us are at Sandbox, and the other three work at Infer. And so the title is about revisiting key decomposition techniques for FHE and how to make them simpler, faster, and a bit more generic. So during the presentation, we'll tackle various aspects of lattice of FHE, so external products, auxiliary gadgets, and we'll see that something that was long forgotten, like base 2K representation of big numbers over the torus, are now coming back as a result of this work, and we'll discuss some consequences on the API and for so FHE for backend developers, for library developers, or for compilers. So let's start the presentation with a small prelude, so some background and some notations. So as you know, so TFHE, so the T in TFHE means torus. And basically, TFHE has been built on a variant of the learning with error problem that is more continuous, that is with only two parameters. And so basically, many people here should be familiar with the learning with error problem. So you have three parameters, one modulus, one dimension, one secret standard deviation. And basically, the LWE problem is that you are given a list of samples, A and B. So A will be a vector, B will be a constant modulo Q. And B is of the shape, the secret times A plus a small error modulo Q that is usually a discrete Gaussian. And yeah, given an arbitrary number of these samples, the LWE problem is to find the secret vector S. So the torus version of the same problem is basically the same rescaled modulo 1 over the real numbers. So it's like if we divide everything by Q and we even forget about Q. So we work on the continuous torus that are every real number, every fractional part of real numbers. So again, we now have only two parameters, n sometimes refer to the dimension. I prefer that n refers to the entropy of the secret, the number of bits in the secret, and alpha, that is the noise rate. So again, in the TLW sample, A will be a vector of elements in the torus, and B will be a single torus element. That is the secret times A plus some continuous Gaussian error modulo 1. And again, the TLW problem is to find S. So these two are the scalar variants of the LWE problem. It works also over rings. So if we want to use ring, usually we add the letter R in the title. So LWE becomes ring LWE, and TLWE becomes torus ring LWE. Something I also like about all this problem is that to study it from a geometric perspective. So there are lots of lattice-based problems that are in the unique domain problem. So it means for all of these problems, LWE, LWE small key, the hidden number problem, the group LWE, TLWE, the subset sums, guaranteed distance decoding, etc. They are all part of the same family of lattice reduction problem, and essentially from asymptotic polynomial point of view, their security are all equivalent. But there are a few differences between those. So some problem will use binary coordinates, some problem will use a large number arithmetic, like the hidden number problem. Some problem will have samples, like all the ones that are on the top. Other will have just a fixed dimension, like the subset sum and guaranteed distance decoding. So if we want to make a sense of all of that, basically we have to find something that is in common with all of these problems. And basically there are two principal degrees of freedom that all these problems have in common. They are all built around the secret. So for the secret, we can look at the number of bits in this secret. And basically, it's very simple. The more bits we put in the secret, the more secure it is. And the second degree of freedom is the measure of uniqueness of this problem. So basically, in general, I cannot create an instance of this problem without first generating the secret, and then once I have the secret, generating an instance of my problem. And it means that if I draw something that is completely random, usually it will not be an instance of my problem. So I can measure, I can play a game like draw some uniformly random instance and reject them until I get an instance of my problem. And basically the rejection probability, or the probability that I keep an instance, I can use that as a measure of uniqueness. So, and all these problem of one and the measure of uniqueness is famous for all of them. So those that are based on lattice reduction, the measure of uniqueness is usually called the approximation factor. For LWE, it becomes the noise rate. And in TLWE, it is also the noise rate alpha, that is the second parameter of the problem. And so as I said, all these problems are equivalent, and once we decide to compare them using these two metrics, so the secret entropy and the uniqueness, there is something that is actually very interesting here, is that TLWE has one very nice particularity. It's the only problem for which if I provide a TLWE oracle, I will be able to solve all the other ones without any overhead. So in some sense, once I use this metric, it makes TLWE, even with binary key, one of the hardest problems of all this family in practice. So it's true that originally the first security theorem was worst case to average case reduction to LWE with full key, and then a proof that full key and small key was equivalent, and then some encoding that would show that small key, binary key, ternary key, small key, as long as we preserve the entropy, are more or less equivalent. I hope that in the future there will be more direct reductions about that. So yes, in TFHE, everything is based on this TLWE problem. And of course, we can be scared at the beginning of using something that is continuous, that is infinite. But if we look at what we do with real numbers, for example, when we want to compute the volume of a ball, we say it will be something like P times R cubed times a constant. And the fact that pi, for example, is an irrational number is actually not scary. We can, once we have the formula, we can actually take any approximation of pi, like 314, 314.15, or the double precision version of pi, that is another approximation, or a continuous fraction. And the thing that is beautiful is that once I have a formula to evaluate, it doesn't matter which approximation of pi I'm using. I will always end up with the right result. So in the torus, it's exactly the same. Even if the torus is continuous and infinite, we have to remember that at all time, elements can be approximated. So that's something that is in common with all lattice problems in general. And everything is numerically stable. So once I use an approximation that is within the noise, all the formula that I will apply will lead to the same decryption in the end. And if I approximate a ciphertext, I will never lower the security. So from a geometrical point of view, basically, TLWE is an ideal scenario to use floating point or fixed point arithmetic. And yeah, we would really need some compelling reason to exit that and to try to use modular arithmetic instead. So yeah, the thing that is very important from the philosophy of TLWE is that everything derives from the noise rate. So always remember the decryption formula B minus SA. If we want to have an output that is known within alpha, it means that, for example, the term B of LWE needs to be known within plus or minus alpha, and A should be known with a little bit more precision. So usually alpha divided by the norm of S or alpha divided by square root of N. And that's the guideline. So we have to deduce the precision that we need from the noise rate. And if the noise rate changes, like if I do additions, linear combination of homomorphic ciphertext, the noise will increase. Whenever the noise increases, it means I need less precision, so I can just drop the last fractional digits. And yeah, so that was just to give the geometric intuition between TLWE, why we only have 2 parameters and not 3. And yeah, the important thing that the noise is really the key, and everything derives from the noise. So we can now start studying the parts of the paper. So on the first part, I will talk about external products and a concept that 2 half products make a whole. So 2 half make a whole was a title about garbled circuit at some point, where in this garbled circuit world, they realized that 1 binary gate could actually be cut in 2, and there was some improvement that came about that. So here, the same idea works for homomorphic external products. So in the Chimera work, the external product is the source of everything. So we have at the beginning ring LWE ciphertext. So ring LWE supports addition, subtraction, linear combination. On top of that, we have the GSW external product. So it means if I have a small secret integer polynomial A, the external product will allow me to compute A times X. So it's like a pre-computed external product by a secret integer polynomial. And once I have this external product, I can apply it in 2 ways in the homomorphic world. Either my secret is 0 and 1, and that leads to the CMUX gate, and then to the blind rotate, and the bootstrapping of TFHE. And the second possibility was to set the small secret as the key of the ciphertext. And then it means that I am able to evaluate polynomial in the secret key. And evaluating polynomial in the secret key is really the central concept in BFV and CKKS to be able to get the internal products. So it leads on the BFV side, if I discretize the torus, to arithmetic modulo P. And if instead of discretizing the torus, I limit myself to a small ball in the torus, to the arithmetic over fixed point plain text. So yes, there are a lot of applications of this external product. So the CMUX, automata, bootstrapping, lookup tables. In these last 4 years, there were many other that came out. PIR, so private information retrieval, is when you have a public database and a secret index, and you want to do queries. Then this programmable or functional bootstrapping that would have consequences in logreg or CNNs. And yeah, the application of the external product to be able to use the internal product. So that was something that was introduced in one of the first version of Chimera. So that was an interesting idea, but yeah, something looked a little bit overkill on that. So basically, how does internal product work? So we have as input two ciphertext, so ring LWE ciphertext, let's say A, B, C, D. So these are ciphertexts of degree 1, so it means the decryption function is a degree 1 polynomial in S. So B minus SA to decrypt the first one, D minus SC to decrypt the second one. And basically the idea of this internal product is that at first, I will do some bilinear functions on the coefficient and obtain a ring LWE polynomial of degree 2. So EFG, and if I want to decrypt it, I would have to compute G minus SF minus S square E, so a degree 2 polynomial in S. And to come back from degree 2 to a degree 1 polynomial, the original idea that was presented was like, if I look at 0E, it really looks like a LWE ciphertext but instead of being encrypted with the key S, it was encrypted with the key S square. So the idea that was presented was kind of key switching idea, where we would replace the key S square by the key S. And that's what's called the linearization technique. So with this notion of just replacing the key. In Chimera, it was more an arithmetic approach that was chosen, so something that derived from the external product. The external product was a secret multiplication by S, so once I'm able to evaluate a secret multiplication by S, I'm able to compute any polynomial in S. And if I apply that to the same ciphertext 0E that encrypts SE, and I multiply it by the secret S, it will encrypt S2E, which is the last term. So the external product was the arithmetic interpretation of the relinearization. On one case, it was a key switch, on the other, it was a product. But the sad truth about all that, and here it's in both directions, but it was more important for the external product, is that when we were doing that, we were applying the secret product to a ciphertext where 1/2 of the ciphertext was 0. So basically, it was a bit bad because we had a very huge GSWE ciphertext, and we use it to multiply it to something that is known to be 0. So yeah, it gave the impression that half of the ciphertext was for nothing. So yeah, basically GSW was designed to evaluate secret times secret products, where both terms are secrets. Whereas relinearization would need something like secret times public products. And that's what led to this idea of splitting the external product in two. So the half external product, that is a secret public product, where A is a small secret integer polynomial, and B will be a public continuous polynomial on the torus. And we want to compute A times B. So if we do that, we only need half of the external product. So if I represent the external product by a box square, that the half of it is a triangle with a square. And from the noise propagation point of view, it actually doesn't depend on anything on B because B is public. So we have a traditional epsilon gives big O of n times epsilon. Whereas on the original external product, since B was secret, B also had a noise, and this term would dominate. So we had something that was more proportional to the input LWE noise. So yeah, and the idea is that, so now for the relinearization, we finally have convergence between this half external product notion with the arithmetic interpretation and the relinearization key. So we are really multiplying by S square, where S square is secret. And of course, if we have the original external product, well, one full GSW ciphertext is just composed of two half GSW ciphertext, D and E, and the full external product is just the sum of the two halves. So here, when we see that, that's beautiful on paper, but maybe it's just syntactic. Actually, it's more than syntactic. If we combine that with the approximate decomposition notion that we use in TFHE, and we remember that in ciphertext AB, B needs less precision than A, now we have something interesting because it means that we can parameterize differently the two halves, and because we have less precision on the second one, we can gain one FFT. So the second term will have one less FFT product than the left term, and there that can represent a real gain. So in practice, well, the first thing we did was to apply it to the original bootstrapping. In the original libs, we managed to decrease the 8 FFT to 7 FFT per cycle. And since the FFT is dominant, and we also decreased at the same time the vector matrix and decomposition, overall, that led to something that was already 15% faster. And I'm pretty sure that the same thing will also impact larger precision, like blind rotate, circuit bootstrapping. So that's something that is really worth investigating. So yes, that was for the external product part. So I'd say this is in multiplicative depth 0, 1, 2, where the noise is kind of large. Now, for the second part of the talk, I will study what happens for larger multiplicative depth. So like the ones that are used in CKKS or BFV. And here, it will be about the return of the base 2K representing decomposition. So let's go back to the first attempt that was done on the Chimera framework. So back then in 2019, 18, well, that was actually a pivoting moment for FHE because on there was this side hash competition, and two candidates came out the first year to evaluate logistic regression. On one hand, we had the first Chimera that was trying combining the FHE blind rotate with some BFV style arithmetic to do some iteration loop. And on the other hand, we got the first really efficient full-RNS version of CKKS that came out that was able to unroll the whole logistic regression in a leveled homomorphic encryption way without ever using any bootstrapping. So yeah, at this time, everything was already about the external product, being able to evaluate efficiently the external product. So external product, we have a gadget decomposition that is constituted of small integer polynomial times some fixed GSW key. That was, in the case of the torus, constituted by huge precision element in the torus. So yeah, basically that's the shape of the kind of expression that we have to evaluate. It's a sum of small integer polynomial times huge precomputed arbitrary precision torus thing. And in the first implementation that we tried, so we said, okay, so, native 64-bit will not be enough. We need at least 100 bits. It was more, even more, 1000 bits of precision. So yeah, the first thing we tried was use GMP and BFR. And yeah, if we look at this expression, so ZNX times TNX, yeah, of course, we have to do some kind of FHE to do that because we don't want it to be quadratic in N. But we have the problem that we are trying to evaluate the product of one small thing times a huge thing. And the problem is that if we deal with that with FHE, we cannot take advantage of the fact that this is small. We still need to do the FHE in arbitrary large precision because of this term. And we were losing everything. So basically, yeah, the GMP and BFR code was spending 100% of the time just propagating carries. And that's why, on the other hand, when we saw the CRT-based full-RNS in large depth, CRT doesn't have the problem of carry. It's a carryless multiplication. So yeah, basically the outcome was, yeah, we are just going to give up. We are going to abort the technique. If we are in large multiplicative depth, we are just going to use CRT full-RNS because that's the best thing that can ever happen. I mean, look at this diagram. It's so beautiful, so square. We have CRT on one hand, entity modulo the same modulus. If we want fast multiplication, modulo xn plus 1, we do the entity. And if we are in coefficient space, we can use the CRT representation to do the gadget decomposition efficiently, etc. So I mean, it was so square and looked so perfect that we really thought it was optimal. And suddenly, at FHE 2003 in Tokyo, we heard the presentation of that Yongso did there, and it was a very surprising and breaking news for us. Actually, full-RNS was not optimal, and that's the reason. So it was always about the external product formula. We had the gadget times some fixed GSW key, and if we dig into the CRT representation, so gadgets are always small polynomials. And in the CRT, we had one polynomial mod Q1, one polynomial mod Q2, one polynomial mod QL. And if we want to do that in entity, well, the naive way is we have to take this polynomial and do one entity mod Q1, one entity mod Q2, one entity mod QL to be able to do the first row, the second row, the last row. So that was L square entity in total. And L square entity is exactly the same as if the gadget decomposition is large. So simplified version of the trick of the of KLSS. Well, the solution was actually simple, but for some reason no one had thought about that before. What happens if we forget that we are mod Q1, mod Q2, mod QL? So if we just treat this vector as regular integer polynomial, and because they are mod Q1, mod Q2, we can choose the center representation, so the integer will not be too big. Well, now here it's a completely different picture, because since there is no mod Q1, mod Q2, mod QL, I just have a small integer polynomial to multiply. It's completely different because I can do some classical DFT over the integer and the precision is not that big. I mean, the largest coefficient that can appear in all this product is probably Q squared times L times N. So if I work on the complex FFT with precision this bound, or if I decide to work modulo a completely unrelated queue that is larger than the result, I will be able to reconstruct my result. And yeah, that's really the main idea that unlocked everything, because now it means that on the online phase, I only have LDFTs to run instead of L square. And I can really take advantage of the fact that the gadget is small. So everything that is on the green stuff, remember that it's the GSWE key, so it's pre-computed, it's part of the keygen. Any DFT I run on this part doesn't count in the online phase. So that's, well, the simplified version of the trick. So of course, once we start dealing with optimization, we realize that here there are a little bit more bits than the machine world. So it makes sense to do another decomposition or another CRT on qtils. So one side effect of that is that there is some kind of big bang of parameter in CKKS right now. In 2005, there were 3 parameters in LWE, then 4 parameters, and an exponential number. So if we remember that in theory, TLWE should only have the 2 degrees of freedom and an alpha, that can sound a little scary. But at least it is efficient. So yeah, let's come back to the base 2K representation that we were trying to do before with Chimera. So this sum of gadget decomposition that is small times huge TNX. So if we follow the same principle, why not trying to decompose the huge TNX into digits? So the red part would be the most significant digit, and the blue part the second digit, 2 to the 2K, and then the brown part the least significant one. And actually here I can do exactly the small thing. I can take all these colors and just form a vector out of it, and just treat my product as a matrix, as a coefficient vector multiplication. So then I will get a result, and if I want to construct the final result, I just have to remember this original formula, and the final result will be the red part divided by 2 to the k plus the blue part divided by 2 to the 2k, etc., plus the brown part divided by 2 to the lk. So here, if I look at that much more carefully, what I'm saying here is that I don't need to propagate the carry at all steps. Once I have done my gadget decomposition here and I have the limbs, I can do an entire set of operations. Like here, there is one FFT, there is one product, there is one accumulation, there is one inverse FFT. And it's only after the war that I need to care about propagating the carry to normalize basically my output. So that's what leads to really a speed up that is actually equivalent to the one proposed in CKKS, and exactly for the same reason. Once I've used the gadget decomposition on my GSWE key, I'm back to evaluating small integer polynomial products, and I just need a small precision FFT to be able to get the result. And once I have the result, I do the rounding and the normalization, but I do it only once, and after all the buzz of the arithmetic. I don't have to do any carry propagation in the middle of all the FFTs. So that's the main idea. So it works for external products. So half and full external products. If we base it on the base 2K decomposition, we get something that is optimal. It works also with automorphisms. So if I decide to switch the variable x with some power of x, it doesn't change anything to the theory. We can work with a nice prefix property. So the base 2K decomposition, basically it's like a base 2K decomposition. So if I have a high precision ciphertext and I want a lower precision ciphertext, I can just truncate it. So modulus rescaling is for free. So there is just a minor setback potentially. What happens with the internal product? Do they become quadratic in L instead of linear in the CRT version? And here there is another, yes, so this is the internal product. Basically how two degree 1 polynomial are transformed into a degree 2 expression by doing some cross-term products. And there are two interpretations of the product, the BFV product, that is a Montgomery product over the torus, and the CKKS product, where we pick a sub ring and we round everything in this subring. And yeah, overall, this I end up with sum of one thing and an external product. And the question is really, these two products, do they really become quadratic, or is there a way to do better? And yeah, the trick is actually very simple. When I wrote the base 2K decomposition formula, instead of taking 1/2 to the k and 1/2 to the 2k, etc., I can just formally write it as a formal variable y. And then once I've used the formal variable y, here what I have is just the integer bivariate polynomial. So if I want to evaluate it, I just replace y by 1/2 to the k, and I will have the value. But the thing that is really cool with integer bivariate polynomial is that on this ring there is a product, an internal product, and it happened that because I'm working on an evaluation morphism, this internal product is isomorphic. It's a ring isomorphism with RNX, with the real ring. And because of that, once I am in the bivariate polynomial, I'm able to evaluate the two products that were on the previous slides. Center lift will pass it over the real field, and the same for the rounding. I can take any representative on the real field, and now, because of this morphism, I have a way of doing this multiplication. But now, since I'm in a bivariate polynomial, I am free to do the multiplication exactly as I wish. So I already know that it's a good idea to do a FHE over X. I can also do an FHE over Y and get an n log L multiplication instead of L square. So if I look at what happens on the internal product, basically in the CRT version, there is no carry, so it will be linear ln. In the bivariate case, we will have a L log L in the place. But once we put that in the overall product, knowing that there is also an external product that adds two terms that dominate in the limited development of the function, it only affects the third term of the limited development. So both in theory and in practice, we know that the two approaches will have approximately the same performance. We can prove that yeah, basically the two running time should be up to a factor 1.5 of each other. And if ever one becomes much faster, it means that it's using some acceleration that can be backported to the other technique. So it gives an entirely different landscape of what we thought before. So before, we thought that the only way of evaluating FHE in low multiplicative depth was to rely on double floating point arithmetic with FFT, and the only way of doing large depth was using CRT plus entity. Now we know that it's not the case. Every combination are valid, so the cyclotomic mechanism and the big number mechanism have to be completely decoupled. And yeah, basically, the choice between entity and FFT, it's really up to the backend, up to the hardware manufacturer. They just have to pick one, but there is not one that is better than the other. They will have the same performance. So if, for example, a hardware manufacturer finds that it is better to evaluate FFT because, for example, it relies, I don't know, on optical systems, and optical system use continuous physics, so it will evaluate the complex FFT maybe a little faster than something that is modulo Q. Then maybe the FFT is better for this one. Or maybe for FPGA, it is possible to design a netlist of a circuit that is very efficient for one particular modulus. So in this case, entity might be better. The two choices are valid. And for the front end, it's the same. We have the choice between bivariate and CRT, and both have their set of advantages and drawbacks. The other very good news is that switching between these four representations is very easy because it's essentially an external product. And it happened that the external product is now fast in all the scenarios. So what does it mean? What should be the new backend API? So all of that, so both this work and the work of KLSS this year, it seems to say that the best representation actually for TLWE and GSWE, and yes, LWE and GSW, is to take the gadget representation as the main representation. So instead of taking an arbitrary representation and then finding a strange gadget decomposition that is efficient, actually, let's just take the gadget decomposition as the main representation. So it means LWE will be represented by a vector of small integer polynomial, and GSW by a matrix of small integer polynomial. And the representation doesn't have to be unique. It can be a redundant representation. And the arithmetic between that is, so the main operation is vector times a preprocessed matrix. So that's the one that happened in the external product. Of course, we need to support addition, subtraction. That's usually easy. Automorphism also. Internal product only if we need the BFV CKKS interpretation. And since the representation is redundant, a normalization to keep everything small. And the key takeaway, so for everyone, there is a takeaway. For hardware developer, the choice between FFT and entity is not important as long as we pick one. What is important is the size of the arithmetic that is supported natively. So 64-bit arithmetic is kind of good, but if we had 128-bit floating point number that are supported natively, that would be much better. For library developers, so if we are looking for a junction between software and hardware, or hardware abstraction layer, maybe the gadget decompositions are a good idea. And we have really to make an effort not to expose parameter that the end user will not be able to set. And for compiler developers, well, it's a choice about the front end, so bivariate versus CRT. It's really about analyzing the use case. If there are lots of internal product, and this internal product can be parallelized, like large matrix vector multiplication over ciphertext, maybe CRT is better because there will be a way to amortize the external product. So then having something where carries are efficient can be a good idea. If, on the other hand, there is almost no internal product in the use case, like for example, use case that have only external product in automorphisms, like circuit bootstrapping, trace algorithm, PIRs, or if there are internal product, but they're always used in sequence, then probably the bivariate is better. And one of the additional reasons is that the noise propagation is a bit easier in the bivariate case. There is not this clamping issue that the inputs of CKKS product has to be clamped to an exact level. And I think that's the conclusion of the talk. So I'll be happy to take questions. Thank you.